Welcome to the 6th video of an 8-video series on polar graphing, leminscates. Here's our first leminscate. Notice what's different about this equation is that we have an r squared in it. We haven't seen that in any of the prior videos. I find the most efficient way to graph something that starts with an r squared is to square root both sides of the equation, thus giving us the plus or minus symbol. Now what that means is that we're going to have to graph r equals plus radical 4 cosine 2 theta and r equals minus 4 radical 4 cosine 2 theta. Let's put the minus 1 on hold for now and just deal with the plus 1. We'll come back to the minus later. So we'll ask our usual question, how do changes in theta affect r? Well, to really discover that, because I have a 2 theta here, as seen before in earlier videos, it would be smart to look at theta in intervals of pi over 4, or 45 degrees, until we get to 2 pi. So I'm going to take all these theta values and plug them into my equation r equals radical 4 cosine 2 theta. And I've done that here. Now, just to illustrate one particular example of a does not exist, in other words, a place where there's a certain theta for which r doesn't exist, or at least isn't real, let's examine this algebra. When you get the square root of a negative, it's not a real number, and therefore we say it does not exist, at least in the graphing sense. Okay, now just because r doesn't exist at 2 singular points, that doesn't necessarily mean that there are lots of places from 0 to 2 pi for which r doesn't exist, or maybe it does mean that there are many places. We don't know. So the question we have to ask ourselves here is, out of all the infinite values of theta from 0 to 2 pi, where does r not exist or isn't real because it's the square root of a negative? We have 2 points on the left that we know it doesn't exist, but there may be more. So to analyze that, see if you can follow this tricky logic. When is the square root of a number not real? Well, when the radicand, or a number under the radical, is negative. But when is 4 times a number negative? When the number itself is negative. That raises the question, when is the cosine of 2 theta negative? Well, 2 theta is our radian argument, and if that were to terminate in quadrant 2 or 3, the cosine would be negative. Recall, the cosine is the x-coordinate on the unit circle, therefore the cosine is negative in quadrants 2 and 3. But quadrant 2 and 3 can be represented this way: pi over 2 to 3 pi over 2, but also 5 pi over 2 to 7 pi over 2, and many more if I needed them, which I won't for these purposes. So if that argument 2 theta is anywhere between these values, in other words, if these inequalities are true, then r doesn't exist. Dividing everything in these inequalities by 2 gives me some clarity about theta, and what this means at the bottom left of your screen is that if theta is anywhere in those intervals, then r does not exist. So I'll put r is not real, which is a graphic way of saying it doesn't exist, in those particular regions. Let's go back to the values we have and look where r does exist. r exists when theta ranges from 0 to pi over 4. r goes from 2 to 0 in that case. When theta is between these values, r ranges from 0 to 2, and so on, as we've seen before. So what we've done now is a full analysis of what's happening to r for various values of theta. And of course the question we have to ask is, How is this going to affect the graph? First, let's let theta go from 0 to pi over 4. You'll notice in the table that r is going to go from 2 to 0. Here's r going from 2 to 0. And notice that r becomes undefined in the table from pi over 4 to 3 pi over 4. And you can see that here that there are no points on the graph as theta sweeps from pi over 4 to 3 pi over 4. Now, analyzing the second half of quadrant 2, notice that r is going to go from 0 back to 2 again, which you can see here. Now we've gone out to a theta value of pi. Now let's look from pi to 5 pi over 4. You'll notice that r is shrinking from 2 to 0. Here's r shrinking from 2 to 0. And then it becomes undefined as theta goes from 5 pi over 4 to 7 pi over 4, which is indicated by no points on the graph as theta sweeps through those radians. And once we get to 7 pi over 4, you can see r going from 0 to 2 again here, thus completing the graph. Well, that completes the graph of r equals positive radical 4 cosine 2 theta. But remember, we're graphing that and r equals negative 4 cosine 2 theta as well. And that's the part of the graph that we haven't looked at yet. So in some sense, we're only half done, because there may be points that are on this graph that are not on the graph that you see at the bottom of your screen. Although in this particular case, that turns out not to be true. In other words, if you were to graph r equals negative radical 4 cosine 2 theta, you would get exactly the same points that we just saw for r equals positive radical 4 cosine 2 theta. A larger question might be, when you take the square root of both sides and get the plus or minus symbol, when can you ignore the minus sign, assuming that you're going to get the same points as you would have with the plus version of the graph? Well, that's a question a bit too complicated for this particular video, but suffice it to say, for simplicity, that if you have a 2 theta, it's very likely that when you square root both sides of the equation and get the plus or minus, that you're going to get 2 identical graphs, essentially meaning that you're good enough just graphing the positive one to know that you've captured the points that satisfy both. Here's another leminscate. So here, once again, we have an r squared in our equation. So to simplify the calculations, let's take the square root of both sides, which of course gives us a plus or minus as before, meaning that we really have to graph the collection of all points produced by 2 graphs. But we won't worry about the negative one here for reasons that we just discussed, and we'll just focus our attention on the positive one, because as it turns out, they will give the exact same graphs, and so there's a duplication here that we don't need to worry about. Is that always the case in general, that you can avoid the plus or minus sign and pretend it isn't there? No. But there's something about the 2 theta in these leminscates that makes that possible. So how do changes in theta affect r? Again, since we have a 2 theta here, we're going to want to look at theta in multiples of 45 degrees, which as usual means that we want to find the value of r at all of these particular dividing values. Now, if I were to plug all those theta values into the equation, and of course I didn't show the algebra here, but if I were to do that, then we would get these particular r values. So notice that there's 2 places in this list of discrete points for which r doesn't exist. But of course that raises the larger question, as it did last time. In general, of all infinitely many values between 0 and 2 pi, where does r not exist? So to address that question, let's try to follow some challenging logic here. When is the square root of negative 9 sine 2 theta not real? Well, whenever the quantity underneath is negative. Well, isn't negative 9 sine 2 theta always negative? Actually, no. If the sine of 2 theta were a negative number, this would be a positive number. But it's going to be negative whenever the sign is positive, and the sign of an argument is positive whenever that argument terminates in quadrant 1 or 2. If you think about the sign as the y-coordinate, that makes sense. Quadrants 1 and 2 have positive sign values. Well, quadrant 1 and 2 can be represented as 0 to pi, 2 pi to 3 pi, 4 pi to 5 pi, and so on. These two will suffice for our purposes. And so if that argument 2 theta is anywhere in quadrant 1 or 2, represented this way, then r is going to not exist, or not be real anyways. Dividing these inequalities by 2 gives us the particular values of theta for which r is not real. So looking at the chart, r is not going to be real from theta equals 0 to pi over 2, or from theta equals pi to 3 pi over 2. So now let's turn our attention to where r does exist. R exists at theta equals 0 and r equals 0, but immediately after that it fails to exist all the way until the range from pi over 2 to 3 pi over 4, where r goes from 0 to 3. I'll represent that this way. Then from 3 pi over 4 to pi, r shrinks from 3 back to 0, as shown here. Anyways, you get the idea. Same down here on the bottom. And now, of course, the question is, how do these changes in r manifest themselves on the graph? Notice at theta equals 0, r is defined to be 0, but also notice that by looking at the table that anywhere between theta equals 0 and pi over 2, r is undefined. And we see that here as theta sweeps from 0 to pi over 2, we get no r values or no particular points. Then once we hit pi over 2, r ranges from 0 to 3, you'll notice by looking at the table. And now we're at theta equals 3 pi over 4. Next, as theta goes from 3 pi over 4 to pi, you'll notice the table indicates that r is going from 3 back to 0. And then once theta hits pi and goes all the way from pi to 3 pi over 4, once again r is undefined, so we get no points on the graph. And once theta hits 3 pi over 2, r goes from 0 to 3. And then once theta hits 7 pi over 4, r retracts back from 3 to 0. So let me make some generalizations here. In general, these are the equations of a rose. And I'd like to share some observations with you that I've made over the years. I've noticed that if n the coefficient of theta, is an odd number, then these roses have n petals, or that many petals. The petal is just referring to the fact that these graphs look like flowers, so that's the idea behind that phrase. We saw an example earlier where n was 3, and we had a 3-petaled rose. This is one of the problems we just finished. But I've also noticed that if n is an even number, then the rose has 2n, or twice that number of petals. And this is consistent also with what we saw earlier. We saw this 2 problems ago where n was 2, we had a 4-petaled rose. Here's an example we didn't do, but if n were 4, we would have an 8-petaled rose, 4 times 2 being 8. But if n were 5, then we would only have a 5-petaled rose. So these are observations that I've made, and they might help you understand whether you're getting your problems right or wrong. The only remaining question really is, how is the rose angled? And do the cosine or sine have any impact on that? Well, yes, they do. The things that impact the way that the rose is tilted or angled is whether you have a sine or cosine, and whether your coefficient is positive or negative. But all that stuff you can sort out as you do the examples. But here are the generalizations, and I hope that helps. And that concludes the 6th of 8 lessons.